So we talked about the pH scale, right? And it's related to, it basically gives us an order of magnitude of the concentration of hydronium in solution, right? So the pH scale, this definition, is just an arbitrary scale we made up to give an idea of how acidic or basic something is. If we take our relationship for Kw, what we can do is we can take the negative log of both sides, and it gives us the relationship between two different scales, which will be the pH and the pOH scale, and they just follow opposite trends. So if I take the minus the logarithm of both sides, minus the logarithm of both sides, the way this splits up is we get minus the logarithm of 1.0 times 10 to the minus 14, right? That's the value of our equilibrium constant. That's what stays constant no matter how much H3O plus or OH minus we add to solution. The logarithm of two things that are multiplied by each other split up into a sum of two different things. Right, so when we took the logarithm of both those things multiplied on the top there, it splits up into a sum of each logarithm. That's just the way logarithms work. It isn't something that you should be extremely worried about right now. This is just a mathematical operation. It's a mathematical identity, right? So minus the logarithm of 10 to the minus 14, this is going to give us a value of 14. Minus the logarithm of H3O plus concentration is equal to what? Minus, so what is this right here defined as? Minus the logarithm of H3O plus. What is this defined as? The pH, right? So minus the logarithm of H3O plus is equal to the pH, right? So this gives us that 14 is equal to the pH. And another scale that we can look at acidity or basicity is called the pOH scale. So this is what we're going to define as the pOH. So the pH and pOH are related now by this equation. Where do we get this from? Well, we just get this from the fact that the concentrations of OH minus and H0 plus operate inversely from each other, right? If one goes up, the other goes down. If the other one goes down, the other one goes up. And so because of that, it means we can look at acidity or basicity from either perspective, from OH minus or from H3O plus. And so using these relationships, right, so we get this relationship here. We have the pOH is equal to minus the logarithm of OH minus. This is another definition we're going to be used. The pOH gives us the relative order of magnitude of the concentration of hydroxide, not just hydronium. But those two have to be related because the concentrations themselves are related. And so this is going to give us a series of relationships that we can use to look at and solve for pH, pOH, concentration, and of either OH minus or of hydronium. Right, so this is a lot of kind of theory. We're talking, where does this all come from? That's what we spent a lot of time doing today. So what is the relevant information from what we've taken away? On the next slide, we'll kind of summarize it all into one slide. Let's make sure. So I'll give you guys a second to finish. All right, so what do we have? We have, am I good to go on to the next one? I see. Still writing, Cindy? Good? Okay. So summarizing acidity and basicity. Acidity and basicity come from the ideas of equilibrium, right? Equilibrium of our weak acid or weak base with its conjugate acid, conjugate base, or the concentration, the equilibrium concentration of our H3O plus and OH minus in solution, right? So we have this relationship that Kw is our equilibrium constant is equal to H3O plus concentration times OH minus. We know these ions are important for determining if a solution is acidic or if a solution is basic. Kw is equal to what? 1.0 times 10 to the minus 14, right? At 25 degrees Celsius, right? The only way we change this value is if we change the temperature of the solution. So at 25 degrees Celsius, Kw is equal to this. We then, from this, determined, well, in a neutral solution, right, the concentration of H3O plus has to be 1.0 times 10 to the minus 7, right? And that gave us a middle ground for our pH scale, right? Because this exponent, so in neutral solution, H3O plus is equal to the hydroxide concentration, and those are both equal to 1.0 times 10 to the minus 7. Right? Dealing with these numbers of 1.0 times 10 to the minus 7 are very small numbers is not very helpful, right? It'd be easier to look at some arbitrary scale to give us what is acidic and what's basic. So from this, we define two different scales. The pH scale, which is related to the logarithm of the hydroxide or hydronium concentration, and the pH scale, or the pOH scale, which is related to the logarithm of the hydroxide concentration. And because these concentrations are related to each other by this equilibrium constant, that means that the pH and the pOH have to be related to each other as well. And so we showed that these can be related to each other because the pOH plus the pH is equal to 14. And so if that's equal to 14, then if you're given the pOH, you can always find the pH. One thing that we didn't show is what if you're given the value of the pOH and you want to find the concentration? Right here, we're given the concentration and we can find the pH. This is what we plug into our calculator right here. Does anyone know how we would isolate the H3O plus there? How do we get rid of the logarithm? Yeah, we raise both sides into the exponent of 10, right? This is a log base 10, so the way we cancel out a logarithm is first we get rid of the negative side on each side, so we get 10 to the minus pOH, or pH, sorry, is equal to the concentration of H3O plus. So all we did there is just introduce a little bit of algebra, and you can do this for both pOH and pH. And I'm going to highlight this one in red because this indicates that these two are important and related to each other. Right, so each of these gives us a relationship between the pH or pOH and the relative concentration of H3O plus and OH minus. And so if we have two scales, all right, we have our pH scale. Actually, that's a little low. I'll do this on the next page. All right, so this essentially gives us all of the relevant equations that we need for acids and bases. Right, we have our Kw relationship, our pH or pOH, then we also have our relationships for the pH. Right, these are basically our 6 important relationships for acids and bases. Meaning if you're given the H3O plus concentration, you can calculate the pH and then the pOH using any different order of these operations. And so what you'll find with a lot of these problems is that there's often multiple times that you can solve them and they'll give you the exact same answer, right? For example, if I want to go from H3O plus concentration to the POH, I can use H0 plus to calculate the pH, right? If I'm given this, I can calculate the pH using the H0 plus, and then plug that into here to solve for POH. Summer?
Where it says a neutral solution, is that H3O, what's in the middle of this bracket? Is that equal?
Those are equal to each other in a neutral solution, yeah. Or, if I'm given the H0 plus concentration, I can use my relationship for Kw to find OH minus, then use that in my equation for the POH to find the POH directly. No matter which way you do this, they will always give you the same answer. All right, anyone right? And so this gives us two opposite scales. We can have the pH scale. If something is acidic, what should we have for a value for the pH? Yeah, close to 1, right? As we get to 1, we're more acidic. As we get to 14, we're more basic. And neutral value should be what? 7. Right? Neutral value should be 7. On the POH scale, a neutral value should be what? What do you guys think? It should also be 7, right? The neutral value doesn't change because that's our midpoint no matter what. If we have a larger concentration, right, that means our POH is going to get closer to 1 as the concentration of OH minus gets closer to 10 to the minus 1. That'll be basic on this side now. Right, so this is basic because our OH minus concentration is large. And then if we go up to a value of 14, that's going to be considered acidic because since OH minus is small, right, 10 to the minus 14, very small, what has to happen to H3O plus? It has to go up to compensate, right? So then that's an acidic solution where we have more H3O plus than OH minus. 7 is the switching point. So this gives us the relative scales for pH and POH. And so we'll probably do one example problem on Wednesday to kind of get the lecture started. But there's also plenty of problems in the rest of these notes that go over different ways. If you're given a concentration, you can use that to find the pH, and you can use the pH to find the POH, and vice versa, right? So a lot of these problems are just going to be identifying which of these equations you will need to use and which steps you'll have to use to get to either the POH, the OH minus concentration, or the concentration of H3O plus, right? Really, we're just looking at two different concentrations, and everything else is derived from that. Okay. All right, so I just wanted to make sure that we introduced all of that. Let's just do one quick example problem. So here we're given an OH concentration, or sorry, we're asked to find the OH minus concentration in a solution which H3O plus, where we have a concentration of 2.3 times 10 to the minus 4 molar, right? So first, and then it's asked, classify the solution as acidic or basic. So if we were to classify the solution as acidic or basic, we can even do that before doing any calculations right now. Does anyone have any idea how we would do that?
OH negative would be to the power of 10.
Somewhere around there, right? If OH minus concentration is less than H3O plus concentration, then we have an acidic solution, right? And if OH minus concentration is larger than H3O plus concentration, that's a basic solution, right? And so we can always compare, what's the neutral value? 7, right? Which means that what exponent should be 7? if OH minus or H3O plus exponent is 7, that means to get a ratio where the total product is going to be 10 to the minus 14, right, kW, the other one has to be 7 as well. That's why it's defined as neutral, is because you have equal concentrations of both. So what you can do before even looking at or calculating anything for acidity or basicity is you can look at this exponent. How does 10 to the minus 4 compare to 10 to the minus 7? Is it larger or smaller? It's larger, right? And if our OH minus concentration is larger than the neutral value, the other way. OH minus, right? Oh, sorry, this is, you're right. You know, you were right. This is H3O plus, right? Our H3O plus is larger than the neutral value, then it's acidic, right? Because if H3O plus is high, what has to happen to OH minus? It goes down, right? So if this is 10 to the minus 4, around what magnitude do you expect the OH minus concentration to be? Yeah, 10 to the minus 10, around there, right? Because but when you multiply them together, they have to equal the ion water product constant, or the equilibrium constant, Kw. Right? So this means that the solution is acidic. But we can calculate this explicitly. We don't have to do this beforehand, right? Let's say, okay, I don't want to think about it, you know, qualitatively. I want to calculate this exactly. What would I use to relate the concentration of H3O plus and OH minus? What equation from these relationships relates those two quantities? We have 1, 2, 3, 4, 5, and then 6. Which one relates the concentration of OH minus and H3O plus? 2, I don't see any OH minus in 2. 6 could if we rearrange it, but yeah, number 1 would be the simplest one, right? We have both OH minus and H3O plus in that equation for equation 1, right? So this is what we'll look at. So if we have Kw equals H3O plus times OH minus, what values do I have already in this equation? Yep, I have my H3O plus, and then what else do I have? Kw, right? Because Kw is always constant, right? Unless we change the temperature, Kw is constant, right? And Kw is equal to 1.0 times 10 to the minus 14. All right, so I plug in my values, 1.0 times 10 to the minus 14 equals 2.3 times 10 to the minus 4 molar times the concentration of OH minus. And I just have to isolate this, right? I divide both sides by my H3O plus concentration, 2.3 times 10 to the minus 4 molar, 2.3 times 10 to the minus 4 molar. These cancel out on the right side, and this becomes OH minus is equal to, and then if I cancel, should use my calculator. Just trying to get me connected to Wi-Fi again. 1 divided by 2.3 is equal to 0.43 times 10 to the minus 10 molar, right? Because we know we're dealing with the concentration. That's how we know the units have to be molarity, which is just 4.3 times 10 to the minus 11 molarity, simplifying it a little bit. And we see that OH minus concentration, sorry, let me write this a little neater, minus 11. OH minus concentration is smaller than our H3O plus concentration that we started with, so this would have to be an acidic solution. So one thing that's nice about acid-base problems is you can generally get an idea of what your answer should be. It should make sense based off the intuition of the problem itself. right? This is a one-step problem because all we had to do was plug in to KW. What if I asked you to find the POH now for this problem? How would you do that?
Plug it in.
Yeah, we would just plug this value in to then POH equals minus the logarithm of OH minus. Right? And I would just plug this value into there, and that would give me the pH or POH of the solution. And then what if I said, well, now I want to find the pH? How would you do that? We could plug that H0 plus directly into our equation for pH. Or I could take this value, subtract that from 14, and that also gives me the pH. Right? So there's going to be a lot of different ways that you can solve these problems. And so we'll do some examples before the quiz on Wednesday. But also take a look at the acid and base worksheet, see if you can start getting an idea for what those problems look like. And also go over some of the questions ahead of time to study for the quiz on Wednesday as well. I don't want to use up our whole lab lecturing, and I'm sure you guys are tired of hearing me talk. But this is the general idea for these problems. You're going to be given concentration, pH, POH, and be asked to go through a series of steps to get one of the other related variables. All right. Any questions on that? Okay.